Hello there, welcome to another problem session. So today we're going to talk about apparent depth, in these kind of situations where you probably know this is like a fish tank problem, and this is some glass and there is some object, a speck of dust inside the glass, and this may be the same kind of a speck of dust inside the glass. So we'll just make it a very simple so they can follow, and then you want to make it more complicated, maybe you can redo the problem with completely non-numerical way. So let's say this is n, and let's call this this n equals to 1. Now I'm going to do because the object, where the object is, I'm going to call this medium 1 and this will be medium 2. So this will be like n1 and this will be like n2. Okay, so this is medium 1 and medium 2. All right, and here I'm just going to do n1 equals to maybe just all of them glass. Okay, this, consider this to be glass, and we can do 1.5, which is 3 over 2. And so this n1 equals to 3 over 2, and n2 equals to 1. n2 equals to 1. You can do it for all other n values, but n1 equals to 3/2. All right. So how do we, basically what's, when you think about this as an object image problem, then apparent depth is simply the object image distance, and actual depth is the object distance. And in all of this is the same thing. The formula for these guys, you remember, is n1 over p plus n2 over q. See, even if the q is in this medium 1, the formula is n, and then n2 minus n1 over r, where r is positive. If I go from here, look at this. This will be a. So if I look from here, this object from the object side, the interface is concave. So this looks like a bulging out. But where the object is, from the object's perspective, from the medium 1's perspective, if you go there, you hit a hole. Okay, so this is this is concave interface, and that's one of the main mistakes people make. Concave interface when looked from the object. And this will be, when I look at the object, this bulging into it. So this will be a convex interface. From all looks like a concave, but it's actually convex. So R is positive for convex interface, and R is less than 0 for concave interface. So this is the notation for this. All right, and the way we look at this r go to infinity. So how do you get this plane interface? Well, we look from there, as if the radius of this is infinite. So r go to infinity. In this formula, you can see this n1 over p plus n2 over q equal to 0. So we can use the same formula in all of three. All right, so let's do them out. Over here, all we need to know is q. So n1, I'll just take p as this object distance p. In all of this, let's just pick a number. But here we'll need r. Let's say r is 10 centimeter, and I'm going to do the p equals to 5 centimeter. And the same here. So this is absolute R. Absolute R is 10 centimeter. We don't worry about the sign at this point when we do it. And P equals to 5 centimeter. Both cases, all of these cases, we're going to do the same thing. So N1 over P. Coming back to this problem is quite easy to do when you think about this. So this is 5. So N1 is 3/2 plus N2 is 1, and then Q equal to 0. So Q, 1 over Q equals minus 3 over 10. So Q equals to minus 10 over 3. So this is minus 3.6 should continue. So this is going to be negative, means on the same side as the object, so it's going to be here. So the apparent depth is a 3 bar, because it's going to be like this, 3 1/3 centimeter. This is going to be up here nearer. Okay, to do this, we just have to solve for Q, right? So let's look at again. We have a 3 over 2 over 5, 1 over Q. But then on the right side is N2 minus N1, which is 1 minus 3/2. And so R is going to be positive and negative. So from here is concave. Concave is going to be negative. So this is going to be minus 10. So on the right side is minus 1/2. Minus 10 is 1 over 20. And on the left side is 3 over 10 plus 1/10, because 1 over Q, 1 over 10, 1 over 20, I mean. So if we make it 20 here, that becomes a 6. 1 over Q equals to minus 5 over 20, 1 over 4. So Q equals to 4 centimeters. So because the curved surface, this distance is apparent depth, Q equals minus 4 centimeters. So apparent depth is 4 centimeters here. Okay, let me pause. Okay, so this one going to go almost like that, except the sign will be different. All the numbers are the same. 3 over 2 over 5 for N1 over P plus N2 over Q equals to N2 minus N1, which is again 1 minus 3/2 is, but this time when we look from here, this is going to be bulging towards the object. That's convex, so that's 10 centimeters. So this is going to be minus 1 over 20, not plus 120. And this will be 3 over 10, which is 6 over 20. So 1 over Q equals to minus 7 over 20. So Q equals to minus 20 over 7. So roughly minus, if it's 21, it will be exactly 3, minus 3 centimeters. So this apparent depth in this case will be 3 centimeters. So this is how you're going to do apparent depth for interfaces that are different shape. The apparent depth basically is where is the image in particular situation. So this, we're looking for the image distance when somebody's asking apparent depth. It's not more mysterious than that. Okay, so what does apparent depth really reflect? Okay, when you're looking at it, okay, so physics wise, when you're looking at it, we're going to look all of this formula 1 n1 over p plus n2 over q equals n2 minus n1 over r. This formula is only when the angles are small. That's why you have to look at very near the normal about which you're looking at. Okay, so the angles are not very big here. So what you see, apparently this is where you're gonna find it's gonna be virtual image. Object is here, but what you see when you look at in an optical system, what you're looking at is actually the image. So the image is here, and you're going to look directly at the image actually. Same way, if the image is here, object is here looking at, but there's no straight ray from here to here. No such ray. The ray actually bends. If you roll a ray like that, it's going to bend that way. Okay, bend that way. So rays are bent. There's no straight ray to the eye, but this appears in the direction of the straight ray. So the image appears in the direction of the straight ray. Same way here. If I were to look at a ray which was directly towards the eye, that ray will never gonna reach there. This ray is going to go in that direction. So there are other rays which are going in the direction of the eye, but image is in the direction of the eye, is straight direction to the eye. So those are the rays which actually went there. So there will be a ray which will hit someplace and it's going to refract and it's going to the eye. Okay, so that's the physical thing, that when you're looking at something, you're looking at the image. You're trying to look at the object, but the ray bends around, and so you really no straight line goes from your eye to the object, but it goes to the image. That's the physical implication of this. That's why I call it apparent depth, or apparently where the object will appear. But of course the object is not there. And in the fishing, if you were trying to use throw something, javelin or something at the fish to spear fishing or something, you just hit the fish. If you hit the fish directly in this direction, you're going to miss it because the fish is over here. So you have to have a sense of how far deeper the fish actually is if you're going to be succeeding. So you don't strike straight where you're looking at, but you strike a little bit below if you have a chance of successful catching the fish or hitting the fish. Okay, so I'm going to stop here. I'll see you in another video. Bye.